All right, I think I'm going to go ahead and get started. It's a couple minutes after 2, so welcome everyone. For those of you who don't know me, as Paula said, I'm KaChun Yu. I'm the resident astronomer, the only person in our space sciences department at the museum. And when Paula asked me if I wanted to do this lecture a couple weeks ago, and she even suggested the title, Evolution of the Universe, you can tell that it hasn't changed. I hesitated because I thought, well, I'm an astronomer, but I'm not a cosmologist. So, technically I don't really know anything about cosmology. And I'm definitely not a biologist. So I really don't know anything biology. But I'm asked to speak on Darwin Day, so you'll probably have the least qualified speaker of today during any presentations. So we'll see how that goes. But after I give it some thought, right before I said yes to Paula, I realized, well, if you think about the evolution of the universe and cosmology, it turns out that there are some connections that we can make to Darwin. So that's something that I'll talk about towards the end of the presentation. But for the beginning, what we will talk about is the evolution of the universe and how it got to what we see today. And so obviously what we want to do is, we know what the universe looks like, and from the Earth out into the solar system. And so what we need to be able to explain is how the universe got to our planets in our solar system, along with all the asteroids and meteorites and comets and other debris. And also, as we keep zooming out, we know that our sun is just one of hundreds of billions of stars in our Milky Way galaxy, and our Milky Way is part of this cosmic web of clusters of galaxies, superclusters, that fill out the observable universe. And so how do we explain everything that we see based on our knowledge of physics? And so that's what a lot of astronomers are working on. That's what cosmologists work on. And it turns out that a lot of physicists do this type of work as well, because what we're all trying to do is to use our understanding of the laws of physics and our observations of the universe to try and explain how the universe got to what it is today. And in the places where our understanding of the laws of the universe are a little bit patchier than in other places, we can actually use our observations to help constrain our ideas about what the laws of physics must be. And so if we go back all the way to the beginning, most of you are aware of that the universe started off in a much hotter, more denser, more energetic state, and it expanded outwards from this initial point called the Big Bang. And after the Big Bang, people are actually not really sure exactly what the physics describe, but they posit that there must be some sort of theory of everything that occurred very, very early on. So we're talking, an extremely short moment of time after the start of the universe, 10 to the minus 43 seconds. For those of you keeping count, that's 0 point, and you have 42 zeros and then a 1 at the end. And nobody knows actually what the equations are, what that theory is. This is a hypothetical theory that physicists think should exist that can describe all the how energy and matter originated and or how it operated at that very early time. But as the universe expanded and cooled, what happened was that these forces, there are actually 4 fundamental forces in the universe today, that they started to manifest themselves. So gravity split off from the other forces very early on. And then later on, you had the strong and electroweak force also splitting off. And the electroweak further split off a little bit even further into the future, 10 to the minus 12 seconds. So that's like an eternity compared to the 10 to the minus 35 seconds. But today we have gravity, strong force, weak force, and the electromagnetic force. But all those were unified very early on. And then something amazing happened called inflation. And physicists aren't very imaginative because all it means is that very early in the universe grew in size. And so this started about 10 to the minus 35 seconds. And by growing in size, that meant it started off about 100 billion times smaller than a proton. Extremely, extremely small, 10 to the minus 26 meters, and then it grew that fraction of a second to something that's roughly a meter in size. You think, well, is that really that big, or is that big of an expansion? And the equivalent to this is if you took an ordinary person and you grew that person to something the size of the observable universe. So that's how big our universe grew in that when inflation started, and inflation ended at about 10 to the minus 32 seconds. So because this is a 20-minute talk, I'm not going to be talking about why we think this happened and what the evidence is for it, but feel free to ask me or come talk to me afterwards. And after inflation ended, then the universe expanded at a much more leisurely rate, at the rate that we see today, although it started accelerating about 5 billion years after the Big Bang. But we won't talk too much about that either. As the universe expanded, it also we also now understand that the makeup of the universe. So it turns out that normal matter, the matter that we are all made out of, consisting of protons and neutrons and electrons bounded together into atoms, that's less than 5% of the matter energy density of the universe. And over a quarter of the universe is made up of this mysterious dark matter, which unfortunately we still don't know what that is. And then just under 70% is made up of this even more mysterious dark energy, which pushes the universe to expand even faster. And we have even less understanding of that. So the physicists and cosmologists have a lot of work to do. And maybe if we give this lecture next year, there might be a marginal better understanding of all this, but I wouldn't bet on it right now. The elements started to appear after the first 3 minutes. So as the universe continued to expand and cool off, it got cool enough for the protons and neutrons to actually start binding together to form atomic nuclei. And so that's where the vast majority of the hydrogen and helium in the universe was created in those early first minutes. And after about 20 minutes, the universe expanded enough that the reaction rates, the chance that random particles will bumble into each other to create your atomic nuclei, the chances of that dropped, and so elements basically stopped forming. So there was a smidgen of lithium that was created in the Big Bang, and you can see that there are other processes that can create more helium and more lithium, but for the most part, most of the helium was created in the Big Bang, or in the aftermath of the Big Bang, and all the hydrogen was as well. And so now, as the universe continues to expand, and now we're talking about tens of thousands, hundreds of thousands of years, millions of years, and the gravity started to pull matter together, and the dark matter, because it was the more dominant form of matter, it actually pulled together first into dark matter halos, and then normal matter started to fall into it. And those are the seeds of the early galaxies. Within the first couple 100 million years, you had the first stars starting to shine, and then those started to show up within the first galaxies. And we have evidence that within a billion years after the Big Bang, some of the oldest stars that ended up in our own Milky Way galaxy were starting to form as well. So the rest of the periodic table of elements were filled in basically by stars. So once you started having stars, massive stars would blow up in supernova explosions. Even the less massive stars would blow up in much less violent explosions. But in the course of their deaths, these stars would create new elements. Also, during the course of their lives, they would be creating new elements as well. But they would expel those heavier elements back into the interstellar medium once they were gone. And they would then basically repopulate the interstellar medium with heavier elements that would then go into the next generation of new stars. And so as more and more stars formed and new generations of stars forming, you would get better chances of creating planets, and then eventually life. But what is really interesting here is that if you look at this table, which shows you the fraction of each element being contributed by each of these different processes. So, for instance, we can look here. This is gold. That's gold, right? I'm not a chemist either. But you can see that most of this is yellow, and yellow stands for emerging neutron stars. So if you have any gold jewelry, that tells you that more than 90% of the atoms in your gold wedding band, for instance, actually came from the explosion when two neutron stars merged together. So pretty much everything that in our bodies and everything around us has a cosmic origin, some in more surprising and interesting ways than others. So how does this actually work? Well, this is a numerical simulation of what an expanding universe looks like. So you have the universe expanding, but you also have gravity pulling in matter. And so we have a galaxy at the center of the simulation, and it's pulling in gas, cooler gas from the intergalactic medium that's shown in green. And as stars form, they have propulsive winds, they have supernova explosions, and that also pushes out super hot heated gas at millions of degrees out. And so that's the red. So you can see red material being pumped out of the galaxy, cooler green gas falling into the galaxy and forming stars. So as galaxies grow over time, being fed by gas from elsewhere in the universe, you can get this very complicated dynamic situation where material is exchanged between the different mediums, and you have stuff being expelled out and then later falling back in. But overall, the structure of the universe is being driven by gravity. Gravity is what is pulling all this together. In the end, what happens is you get basically galaxies and clusters of galaxies forming at these sort of nodes. So each of these sort of bright spots is a cluster of galaxies or one supermassive galaxy. And you have material that's being fed in via these filaments. And then you also have these gigantic cosmic voids, which today are hundreds of millions of light years wide. And so at the same time that the universe is expanding, you're also seeing this superstructure, this filamentary web of the universe being built by gravity, where you have galaxies and galaxy clusters along what are basically at the edges of these gigantic soap bubbles of voids. Now, individual galaxies grow from the mergers and collisions with smaller galaxies. So you can imagine if we are looking at our Milky Way galaxy at the bottom, it resulted from the merger of lots of smaller proto-galaxies that merged over time into medium-sized galaxies, and those grew, again, via gas falling in from the intergalactic medium, and over time this would merge to form our Milky Way. And so here is another simulation showing how this would work, where you're seeing lots of galaxies all interacting. And again, the forces that are driving this, the primary one, is gravity. And so you have galaxies that are orbiting one another via gravitational forces. And within each galaxy, you can even get a sense of the rotation or the orbiting motions of stars and gas within those galaxies. And over time, the larger galaxies swallow up the smaller ones, and they grow bigger and bigger. And even today, these mergers are happening. So the mergers peaked earlier on in the universe, but there's still lots of galaxies. And we can show that via computer simulations that different stages of this merger scenario between two spiral galaxies actually show up in our sky. So these mergers can take hundreds of millions to billions of years. So when we look out, we only see a snapshot in time. We can't actually see these galaxies actually change appreciably. But because we can observe hundreds of thousands, millions of galaxies, we can find examples of galaxies in different stages of this animation. So they're able to freeze this animation and show how this merger can actually correspond to different galaxies that we observe. So this is a really good example of how our observations drive our simulations, but then we can look at our simulations and confirm that our observations and our simulations agree with each other. All right, so let's dive in a little bit deeper into a galaxy like our own Milky Way. This is M51, and you can see that the galaxy has lots of stars. That's the not just the bright star-like things along the spiral arms, but anytime you see sort of a glow here, and this is a satellite galaxy, that's in the process of colliding or merging with this main galaxy. But anytime that you see a faint glow, that glow is from the light of millions of stars, and each of them are too faint or too far away to be resolved, but they all together aggregate into a glow. And you do see what look like individual stars, but those are likely to be stellar clusters, bright clusters. But you also see lots of dark regions. And so following the spiral arms, you see these dark clouds, but there are also these kind of reddish blisters that line the clouds. And each of these blisters is a star-forming region. So parts of the cloud can gravitationally collapse. They become unstable and collapse. And in each of these red spots, you can have tens of thousands of stars forming. This is a distant galaxy, but more closer by within our own galaxy, we can see what some of these blisters might look like. So this is the famous Eagle Nebula, which many of you might remember as containing the pillars of creation. And the pillars are right here, so they're really tiny. But there's a set of massive stars up here, and these massive stars, they're much bigger, at least 8 times the mass of our sun, and they burn brighter. They pump out a huge amount of ultraviolet radiation, and they also have these very propulsive winds. And the radiation and the winds from these stars actually excavate out a cavity. I mean, you can get a sense that there's a lot of dark gas here, but these stars have blown out these big bubbles that's filled with 10,000 degree gas. And the reason that the pillars of creation are shaped the way they are is because, again, of the erosive effects of the UV radiation and the winds that have basically destroyed a lot of the surrounding gas and have left kind of the densest pillars left. But you can see that this is a very dynamic process. Most of the stars that you see here are young. They were born from this cloud, and as these winds continue to disrupt this cloud, at a certain point, the gas won't be capable of creating more stars. But again, we can run simulations to see how this can work at those very small scales. So this is a massive star that's in the center of this simulation, and you've seen the effects of the winds from this star, basically, again, excavating out a cavity in that gas cloud. And so you can imagine over the course of tens of to hundreds of thousands of years, this, along with perhaps a dozen other stars like it, could create the cavity that you see in that previous picture. And so what happens over time is that if you have a galaxy and you have lots of star formation taking place along the spiral arms where the molecular clouds are, you can see star formation taking place. You can see stars winking in and out of existence as the most massive ones explode in supernova after only a few million years. And so again, there's this process of where you're injecting energy and matter and heavier elements that were created from those stars and enriching the interstellar medium. That gas eventually finds its way back into the molecular clouds, and they form the next generation of stars. Now, if you had asked me just a year ago where the elements from our sun and our solar system come from, I would have said, well, they would have come from supernova that spread the elements out into our galaxy, like I've been talking about, and they would eventually find their way to the gas cloud that our sun was born from. But it turns out that people who actually do this, who actually study this and create simulations of this, the elements can come from much, much further away. This is actually from a planetarium show at the California Academy of Sciences called SPARC. And what this is showing is it's starting at the start of the solar system, and it's going backwards in time. So every second, we're marching backwards by 20 million years, and you're seeing that although a lot of the elements do come from the disk of the galaxy, a lot of them come from a lot further away, hundreds of thousands of light years away. So they're coming from gas clouds, they're coming from smaller satellite galaxies, and that again tells you that the stuff that we are made up of might have had a lot more interesting journeys getting to our solar system than where they've been since. But this is a pretty amazing visualization of how our galaxy and our elements have evolved over time. And then finally, I'm going to talk a little bit about lower mass star formation, because it turns out that although the vast majority of star formation takes place in these places where there are lots of massive stars, it's in these places where you don't see the massive stars where you can study star formation a little bit better, just because the massive stars tend to have wiped clean a lot of the evidence for what's happening with the lower mass star formation. But this is a cloud called NGC 1333. It's about 1,000 light years away, and this is actually an optical image taken from the ground down in southern Arizona, and you see again evidence of lots of obscuration due to the gas that the cloud that contains these young stars. So this cloud is actually obscuring a lot of the starlight. But you also see evidence of what looks like disruptions in the cloud. You can see sort of this reddish jet, and there's gas blowing here that looks very disruptive. And if we switch over to the infrared, what we see are lots more stars. And so in the infrared, we're actually peering through a lot of the obscuration, seeing through the veil of gas and dust. And if we go even further into the infrared, into the mid-infrared, you can see the evidence of jets emanating from these young stars. So these stars are typically will end up being not much different than our sun, so just an average normal star. But even for these solar-like stars, they very early on can have these propulsive jets that inject energy into the interstellar medium or into their cloud medium, and they're similar to what's happening with the massive stars. They're breaking the cloud apart, and you can even imagine sort of tunnels being dug by these jets as they're breaking through the cloud. And so again, there's always a simulation for what's happening. And so here is one showing how a gas cloud can condense and gravitationally collapse to form new stars. And as these stars evolve through their protostellar stages, you'll start to see the jets appearing. And so here they are. They're starting to squirt out. And again, this is, even though matter is falling in towards the central star, a lot of it ends up getting ejected. So the star formation is a process that in some ways is self-limiting, just because these clouds eventually break up due to the star formation process. Right, so that takes us to the birth of our solar system. So here we are this is another California Academy of Sciences planetarium show, and we're seeing the disk of material that has aggregated around the early sun. And you can see how material can actually start flowing onto planetesimals, these small precursors to planets. These are different simulations done at different scales, but this shows you the extent of what people who are studying this type of work, what they're capable of. And over time, the planets actually carve out gaps in the disk as they draw in more and more gas. And even after the planets have formed, they can actually gravitationally interact with the leftover debris. And so this is a simulation of what happens to the planets. You can actually see the orbits of the planets are actually changing quite a bit. And planets can even swap positions so that we think, for instance, that Neptune was actually orbiting closer to the sun than Jupiter. And this is all due to gravitational interactions with these smaller bodies. And so even over the course of the history of our solar system has been a very dynamic place. And that leads us to our solar system of today, full of inner rocky planets and outer gas giants, but also a solar system that's filled with comets and asteroids and a lot of this cosmic debris. And that takes us to the history of the Earth. And since I'm not a geologist, I'm not even going to bother really talking about this at all, except there's a wonderful animation that you can see showing the formation of the moon and the cooling of the Earth and formation of the oceans and eventually of biology. And so that takes us back to the question that we asked, that I posed at the beginning. What does all this have to do with Darwin? And I guess, obviously, if you make this linkage all the way to the formation of life on Earth, there is that clear linkage. But Darwin himself, as I understood it, didn't really care for or care much about astronomy. If anything, he was more a geologist than a biologist, because I think he was going to win an award for geology right before The Origin of Species was published. But one of the fundamental changes that he made to the scientific enterprise was the idea that you needed a supernatural explanation for what you observed in the world. And this sort of followed on what Isaac Newton did. So 2 centuries before, Newton had explained how his theory of forces and of gravity could basically explain the motions of the planets around the sun. And so that was a way of removing the supernatural from understanding the motions of these heavenly bodies. And here, Darwin came up with a way to remove that for biology. But I think, this sort of philosophy of how science works obviously infected other sciences. And so for physicists and astronomers today, they look at the universe and they try to explain it based on their understanding of the physical laws. So again, we try not to use any sort of supernatural explanations. But this goes even further than that, because more recently, people have been wondering, why is the universe in some ways so fine-tuned to creating galaxies and stars and solar systems and possibly life? Because it turns out that if you look at the equations for the universe, if you look at how the universe evolved, if you change some of those fundamental constants just slightly, you can actually come up with a universe that is not conducive to forming galaxies or forming stars or even forming atoms. And so if you can't form atoms, then life is out of the question. And so there have been some people who advocate for, who have given this a lot of thought, and they wonder, well, maybe there is a connection to Darwinian evolution, because we know that in the evolution of life, you need two very important things. One is you need variability. You need the fact that in successive generations of life, each generation isn't an exact copy. Each individual isn't an exact copy of its parent or of its siblings, but that there's variability. And when you have that variability, you can have natural selection taking place that can call out members of the species that aren't as fit to survive in a particular environment. And so there have been cosmologists, particle physicists that have speculated that the evolution of the universe might follow along similar lines, where if you posit that string theory is correct, and there's a lot of debate whether string theory is correct or not at all, whether it could be completely wrong, but it turns out that there's a lot of give as far as how variable string theory can be, meaning string theory can also posit different fundamental constants. And if we talked about inflation earlier, where the universe expanded by a huge amount, and if you agree that inflation occurs, then that there are some versions of inflation that suggest that inflation can actually occur continuously, meaning some part of the universe can actually inflate into its own separate universe, and that if you have this huge multiverse of universes, and each of which might have slightly different fundamental constants and slightly different laws of physics, then it it's no surprise that we end up in the one where life has been able to arise. So again, this is all extremely speculative because people have debates about inflation. There are lots of strenuous debates about whether string theory is real or not. But it is interesting to see that there is this possibility that the intellectual tradition that Darwin started might continue today or in the near future with the evolution of our universe. All right, so thanks everyone, and I'm happy to take questions.
That's the universe in a half an hour. That's pretty extraordinary. I'm sure there are lots of questions, so we've got plenty of time. Oh, yeah.
I don't know how this works. Okay. I am curious to know, is there any observable pattern to the distribution of different galaxies at different stages of colliding or not colliding, or is it very random throughout the whole universe?
Yeah, I mean, there's definitely an element of randomness to everything. So that's another key point. When you talk about natural selection, the idea that there's randomness to each generation. Which individual gets slightly different genes, but there's also randomness to how galaxies merge. If you think about, let's see. What's a good way of placing this? I'm trying to think about how to answer your question. There's randomness and also there's not randomness. So what's not random is if you look at the evolution of galaxies from these smaller galaxies early on in the universe and how they grow to much larger objects. If you can mathematically describe the scale or the range of scales. And so one reason why we're confident that dark matter and dark energy is an important part of the universe, and they take up those fractions that we saw in that pie chart, is because if you run cosmological models, you can actually come back with mathematical descriptions of how many small galaxies versus larger galaxies that you get that match reality. And then, as you saw in some of those simulations, you also get the cosmic web, coming out. But as far as whether you get a cosmic web that looks exactly like our local cosmic web in a Milky Way galaxy that looks exactly like our Milky Way with other galaxies around it, that will be due to more random forces. And you can run a really big simulation and look for Milky Way analogs. And people do that, but that doesn't say that you're exactly predicting our Milky Way forming exactly the way it is. Hopefully that makes sense.
Yeah. And I guess just to follow up, I guess I'm curious. I'm wondering if you were to map out a snapshot of the universe right now, would you see a pattern to smaller galaxies at certain distances from a point that's measurable, or are there larger galaxies towards the edge of the universe and smaller ones towards whatever the center might be? Or is there anything like that?
Yeah, so that opens up a can of worms because...
You're welcome.
I mean, so part of the problem, and this is something that I didn't really discuss at all, is that the speed of light is constant, meaning when you look further out into the universe, you're also looking, you're looking further away, but you're looking backwards in time. And so what that means is that if you look at a very distant part of the universe, you're actually seeing that universe, 1 billion years in the past, or 6 billion years, or 8 billion years, or 10 billion years in the past. And so the galaxies at those distances won't be like the galaxies today that are in our nearby universe. But you have to make this assumption that the universe is isotropic and homogeneous, meaning that no matter which direction you look, it's more or less the same. And so even though the universe looks very different in that direction, because you're looking at it 10 billion years ago, you're assuming that, if you were to magically transport yourself to that location, it wouldn't look like what it looked like to us here. It would look like more evolved galaxies that are close to us. So I guess to answer your question, people can mathematically describe distributions of larger versus smaller galaxies, and they can even have mathematical descriptions. If you have a galaxy here, what is the likelihood that you'll find a smaller galaxy some x distance away? And basically we do have a pretty consistent picture, but it is complicated by the fact that when you're looking, depending on where you're looking, you're not necessarily looking at correspondingly the same place evolutionarily speaking in the universe, if that makes sense. Okay.
Other questions? Don't be timid. Questions about?
Yeah, I'm open to even the craziest questions, so don't be scared.
Okay, so dark matter. We have our periodic table of elements. Would it be possible that it's just simply an element that we're unaware of and it's giving off dark energy?
Okay. Yeah, so dark matter, back in the 90s, people wondered whether dark matter might be due to, let's say, a population of small black holes or a population of these compact objects that we weren't observing because our telescopes weren't powerful enough to see these. And they were out there, there's a lot of them, and they were an important constituent of the universe because it's you actually need dark matter to hold galaxies together. When we measure the velocities of stars in orbit around our galaxy, we find that the mass that you infer from their orbital speeds, they cannot be explained by the visible matter that we can observe. So back in the 90s, there was this idea that dark matter might be, small black holes, or there might be a population of planets that were floating rogue outside of any star system. But as our telescopes got better and people made concerted efforts to find dark matter as ordinary matter, they weren't able to do it. And as so another thing that I didn't talk about was the cosmic microwave background, which is the earliest light in the universe. But if you measure and map it and quantify it extremely well, you can actually tease out information about all the different parameters in the universe. And so that is kind of the fundamental reason why we can create that pie chart where you can get down to 0.1%, an understanding of how much normal matter, dark matter, and dark energy there is. So right now, unfortunately, we still don't know whether what that dark matter is. It does seem to be very separate from dark energy. So dark energy is its own thing because whereas dark matter is creates gravity, it pulls things together. Dark energy is actually it does the opposite. It pushes things apart. So dark energy is like an anti-gravity. It causes the universe to accelerate faster. So we think, there might eventually, people might come up with a way to tie the two together, but because they are very different, they must be fundamentally, today, they're different forces that are acting on the universe.
Other questions?
First off, this has been super cool, and thank you for putting it in plain English so that I can understand. I just wanted to ask if you could tell us about what you think might have been the most unexpected or surprising discovery in recent years, and if you could speculate on how that kind of changes what we think about the evolution of the universe. Okay.
Yeah, that's a great question. So I mentioned the cosmic microwave background and how you can, so the cosmic microwave background are photons that originate about 380,000 years after the Big Bang. And as the universe cooled, the light, the photons were constantly interacting with the protons and neutrons and electrons. So they were, everything was so dense that they constantly collided with each other. But as the universe expanded and cooled off, you basically gave enough space to everything that you decrease the likelihood that the photons would interact. And so so the photons were basically frozen in place, meaning they were left an imprint of their last interaction with the matter as the universe continued to expand. And then after that, the matter started to collect into atoms. Okay, the protons would combine with electrons to form hydrogen atoms. So, like I said, we can observe the cosmic microwave background, and from the information in that cosmic microwave background, we can infer the fundamental parameters that make up the universe. So, like the fraction of ordinary matter and dark energy, like we saw in that pie chart. And we can also infer how fast the universe must be expanding in the present day. So that's inferring, the rate of the universe expansion from kind of the edge of the universe, from the beginning of the universe. We can also infer the expansion of the universe by looking at galaxies much closer to us and there's a whole complicated history and subdiscipline of astronomers trying to figure out measuring the distances to nearby and more distant galaxies and using that to infer the expansion of the universe. And people have been doing it for many decades, and in fact, the Hubble Space Telescope is named after Edwin Hubble, who made the first scientific observations showing that the universe was expanding 100 years ago, actually over 100 years ago. And so so there are two ways to measure the expansion, one based on nearby galaxies and one based on the cosmic microwave background. And people have been driving the error bars for both of these measurements smaller and smaller over time. And what's been happening is that the cosmic microwave background, the early universe people are finding a Hubble expansion of 67 kilometers per second per megaparsec. Don't worry about the units, they're meaningless in the context of this talk. But the people investigating the close by late universe are finding a Hubble expansion of about 75 or 76 kilometers per second per megaparsec. And the error bars are in the order of like 2 to 3. So there's, that's a big difference between 67 and 74. For those of you who are scientifically inclined, it's on the order of 4 standard deviations. So that's huge. And so it's like, if you were trying to drill a tunnel through a mountain and one, side starts from one direction and the other team starts from the other direction, and they end up not meeting in the center, in the middle. So that's sort of where cosmology, that's one of the biggest mysteries of cosmology. Why is it that we're getting these very different results for how fast the universe is expanding when you make a measurement at one end of the universe, early in the universe, versus the other end of the universe, late in the universe? And right now, people don't really know. There are people suggest, not quite understanding how the universe has evolved, not quite understanding, perhaps there are errors that are not accounted for, ways that we're doing our observations that people are not fully understanding, that something is still fudging the results. But right now, we don't really know. And of course, the most exciting possibility is that there's something fundamental about the universe that we don't quite understand. Perhaps it has to do with the law of physics that messes with how these measurements are made. And so if that is true, then that's a pretty exciting result, because that will fundamentally change our understanding of the universe. Now, if you've read a lot about the history of science, you know that scientific revolutions do occur, meaning we have these giant phase changes in our understanding where we think one way one day, and then suddenly the scientific enterprise changes direction completely, and our scientific understanding also completely changes. And there are lots of examples of these scientific revolutions, but it's important to note that if you have a completely new scientific understanding, you still have to explain everything that you were able to explain via the old way of understanding. So that's why scientific progress can be very difficult, because your new understanding has to make sense, but it also has to make sense for everything, not just this one little bit that you're trying to explain.
Time for a couple more questions, if there are some. Oh, one more.
There are a lot of questions I could ask, but I guess what I'm really wondering about is, it kind of just to dovetail on what you were just talking about, like these scientific revolutions. Do you feel like what role, I guess, do you foresee AI playing in us gaining a deeper understanding of what's really happening in the universe?
Okay, so AI means a lot of different things. Machine learning was something that people had worked on for decades before this recent explosion in AI, and so I think for a long time astronomers have been using machine learning algorithms for many years to do things like galaxy identification, for instance. So it turns out that astronomers create these surveys where they have these telescopes that just map the sky, and they're robotic telescopes to some extent, and they can create maps of tens of millions of galaxies. But in order to have some understanding of what you can do with these pictures, you have to go in and actually identify whether a galaxy is a spiral galaxy or an elliptical galaxy, or what type of spiral, or some other type of galaxy. And there have been a lot of citizen science, community science projects and you can even sign on now, where you can sign on to a project to do galaxy identification, for instance. And so there are AI projects where you learn from the humans to identify galaxies, and not just current day galaxies, but early galaxies, when because of collisions, the galaxy shapes are really weird. I remember one paper where they actually had the word banana in the title of the paper. You don't actually usually see fruit mentioned in the title of astronomy papers, but that was in reference to the fact that they were trying to identify banana-shaped galaxies, and so you use humans to train the machine learning models, which then can then go out and as you're getting these observations in, you can go out and automatically identify and catalog these hundreds of thousands of objects, or millions of objects. And we actually have a telescope that's coming online in the next couple of years, the Vera Rubin telescope, that will basically be mapping the sky continuously. And so that will actually be generating huge amounts of data, like petabytes of data, and hundreds of thousands, or even millions of new discoveries each night. And you have to automate all that. Machine learning can definitely help you process the immense amount of data that's coming in from observatories. But as far as the intellectual enterprise of trying to figure out these really big questions, why is it that our measurements of the expansion of the universe doesn't agree when you're looking at it from one direction versus the other, or if these other questions about is string theory true, or can you come up with an alternate theory of everything that can explain the different forces early in the universe, that seemed to require a type of imagination and creativity that is very human in the sense that you're taking in a lot of information, but you're not necessarily just summarizing, but you're using your human creativity to come up with something new. So that's something that I'm not sure AI, as it's used today, can really help with. But there are definitely ways in which AI can help with understanding or astronomical observations. And that's a great question.
Thank you.
I think with that positive note, that's a good place to end it, that humans can solve the explanation of the universe. Let's thank KaChun for a really great way to end Darwin Day.
Thanks, everyone.